Very good afternoon, sir. My name is Dhiraj Katole, and I am doing the research under the guidance of Dr. Dhiraj. My research topic is some studies for power quality improvement in distributed system using dynamic voltage restore. The contents of the research objective of the research were introduction about power quality and voltage sag, three-phase DVR controller, and simulation results, modeling of single-phase HV inverter and switch target DQ frame, analysis of injected voltage, angle and active power, different control strategies, various considerations, feed forward control for three-phase DVR, proposed phasor-based control for single-phase DVR, modified distance DQ based controller, SRFP based controller for single-phase, simulation results, and various hardware results, conclusion and references. The objective of my research is to improve the power quality using the DVR distribution system, and also some studies on topology, different types of control design of three-phase and single-phase system, and effect of energy storage device like battery or capacitor. The specific objectives using custom power controller is I have to investigate the power quality related to voltage in distribution system for different types of faults and load conditions, to investigate improvement of power quality in distribution system for different types of faults, load conditions with the application of custom power device like DVR, and investigate the power quality with the application of DVR with the energy storage device like battery or capacitor, and we have to improve the performance in the distribution system. The survey of distribution events has been done in North America and for around 1000 data for about 112 various locations and in the year 1990 to 94, and according to CBEMA curve, Computer Business Equipment Measurement Association curve, among all the disturbance, the event of transient was around 60%, while the occurrence of interruption was 1%, and the occurrence of low voltage is about 26%, and the whereas high RMS is about 13%. 90% of occurrence of voltage RMS lasted for less than 60 seconds. So now as the RMS decreases to less than is a low RMS about 26%. So whenever there is a fault at one of the load, there is decrease in the voltage at the other load. That is called the voltage sag. Voltage sag are characterized by these two equations, whereas ZF is the fault impedance, and ZS is the source impedance. So with the decrease in the source voltage, there is the decrease in the voltage level at the load side. So we have to inject the voltage at a particular angle so that we have to maintain the voltage at the desired reference value at the load side. So this is the pre-sag voltage. Whenever there is a decrease in the voltage, V-sag, you have to inject at a particular angle so that to maintain the voltage at the desired.
So load you are considering as a balanced load.
It is balanced.
That is not the case. Power quality, that is the major problem.
Yes, I have taken both the cases, balanced and unbalanced.
Unbalanced we have taken. But otherwise these derivations are very balanced.
So what is voltage sag? Voltage sag is a momentary decrease in RMS voltage lasting between half cycle to several seconds. It is due to the various faults like short circuit fault, motor starting, switching action, increase in the load, loss or defective wiring or switching action. There may be various economical losses and power loss in the industries and the domestic appliances. So magnitude of voltage sag for different types of fault. Voltage sag for different origin. Here you can see the one indicates the transmission fault. First point, one indicates for the transmission fault. In transmission fault, the deviation is less than 0.2 second. For remote distribution type fault, the sag is not less than 80%. For local distribution fault, the sag is around 50% for duration of around less than 0.8 seconds. And the starting of large motor, there is little bit of sag in the voltage, so we can maintain without a active power injection, short circuit interruption and fuses. There are various devices used for the quality improvement, power quality improvement, like the UPS, like the DVR or SSTC. Whenever there is a fault, the supply line is switched from the sub-voltage line to the other normal healthy condition line. For that, we have to use the solid state transfer switch. But there are various considerations about these devices. The higher rating of the devices are used, like StatCom. If you use the StatCom at shunt for the voltage control, then the rating of the StatCom will be higher, much higher as compared to the DVR. That's why I have concentrated on the DVR, because I can minimize the rating of the DVR and it will be more cost-effective solution for the power quality problem related to voltage. Now there are various locations where we can connect DVR. It is at the medium voltage level or it can be at the low voltage level. So for particular where for consideration for power quality improvement, different types of load can be connected at the distribution end, but the rating of the DVR which is connected at the medium voltage will be much higher, and we require more energy storage device, energy storage device as compared to the low voltage DVR. So that's why I have concentrated on the low voltage DVR first. Now there are various three-phase DVR topologies. We can connect with the three-arm bridge, that is Ghrce bridge, with the help of a transformer. It can be these can be connected with the delta fashion, delta open, or you can connect with the star open fashion, star open winding. So here we cannot inject the zero sequence into the system. With this arrangement, the star open, we can inject the zero sequence into the line. So most of the researchers have now concentrated on the zero sequence component injection into the line. That's why this is the case. We can also go for a edge bridge type connection. We can connect with three different transformers connected with the edge bridge link, and we can, with a common DC link, we can provide the separate line voltage or phase voltage to the different types of fault conditions. This is without the transformer. The advantage of this type of connection without the transformer is we can the system becomes lower bulky. Here the system is bulky without the transformer. But the advantage with transformer is that we can separate out both the power and the control circuit. There is and whenever there is a fault and the interline fault in the DVR and in the VSI, then we can protect with the help of these transformers.
Last 1 minute with practical. So last speed.
But some researchers have also implemented this.
Would you anywhere any manufacturer doing this type of thing?
No, I have not seen this. In the research paper, I have the situation I have seen this. So this is the system under consideration for three-phase DVR controller. Now consider the two parallel loads, where one of the load is the other load and other is the critical load, and I have connected the delta open series transformers. I have created a three-phase fault and other load. Due to this three-phase fault, there is voltage drop in the PCC, power point of power coupling. So this is critical load. I have to compensate the voltage at the critical load. So for this, I have made this arrangement for the DVR, where DVR is consisting of the energy storage device which is connected to the DC link. This energy storage device is necessary because during the compensation, there is decrease in the voltage level of the capacitor. That's why this energy storage provides constant voltage during the compensation period. Where gate bridge VSI is connected, and for the filtering operation, delta type filtering is provided. SPWM method has been used here. Here, whenever there is a fault, then I have converted this ABC to DQ, because this DQ is based on the DC value. So it is more advantageous to find the detection. It is more faster as compared to the instantaneous value. That's why the ABC is converted into DQ, and it is compared with the 90% threshold value. If it is less than the 90%, then sag is detected. It will send the signal to the controller, and in that manner, this complete system gets connected to the critical load. So whenever there is a sag, the sag detector signal becomes high, and the complete controller works. And this is the sag character, where both the actual signal and the reference load signal both are compared, and the error is sent to the PI controller, and then it is again inverse transformed from DQ to APC, and with the reference injected voltage, we can actually control we can maintain the desired load voltage at the load end. These are the parameters which are considered for the three-phase DVR system details. Where this is the 50 kVA system, 10% series transformer reactance, short circuit kVA and base value 415 LC filter. This is the critical load, 10 ohm load is connected. It is near about 16 kilowatt load. Line impedance, both line DC capacitor 500 megafarad, receiving 340 is the voltage provided. The receiving switching frequency is around 3 kilofarads.
Your load is only active load.
Active load, yes. Critical load is the active load. I consider
unity power factor.
yes. I consider initially on the initial base as the active power. So this is the feed forward controller for three-phase DVR ABC is converted into DQ, and for this PLL is used, where PLL gives the continuous angle of the voltage, actual voltage. So this signal is whenever the sag detector detects the signal, the reference voltage, reference supply voltage is generated, and it is compared with the actual voltage. PI controller injects the error, and these errors is converted into DQ. ABC means the instantaneous value, and that instantaneous reference sinusoidal value is compared with the SPWM. It is compared with the triangular waveform, that is the SPWM techniques have it is being used and given to the VSI. These DVR can be controlled by either in the standby mode or active mode. Standby mode, during the standby mode, it will be the energy storage device is getting charged, and whenever there is a sag, it will be converted from standby to active. These are the results of three-phase DVR, where the sag is initiated at 0.1 second. It will be remain for around 7 cycles up to 0.2 second, and this is the injected voltage by the controller through the transformer, complete transformer. So you can see from these results that it is not compensated truly. The load voltage is not completely compensated by this type of compensation, because the energy storage device has the less energy. So due to that less energy, the voltage goes on increasing, average injected voltage goes on increasing, goes on decreasing. That's why it is not compensated to the desired value. So whenever the battery is completely charged, so in that injection of voltage by the DVR will be completely to a desired value of load voltage. Here it is compensating to a complete desired value of load voltage. See here, the load voltage, the injected voltage is nearly constant, and it is maintaining the constant voltage, load voltage, reference voltage at the load end. So energy storage device has the more effect on the compensation of the device. That means apart from reactive power, active power injection is also needed by the device. These are the results for the multi-level inverter. I have considered the single phase as this cascade inverter. I have simulated the results for 5-level cascade inverter, 7-level cascade inverter. Similar type of results have been obtained for these feed-forward control installations. Now, in this 3-phase ABC to DQ transformation, 3 phases are converted into 2 phases, which are in the stationary reference frame, where both these components are rotating. These rotating components are converted into fixed components, where the frame is rotating, components are fixed, that are the DQ components. And when these DQ components are combined, the vector addition of these VD and VQ gives the actual voltage, which is having a phase angle theta with the reference value, if you consider particular dx as a reference value. So this voltage VD is fixed, VQ is fixed, it is not changing. So since the 3-phase controllers has various drawbacks, because there are various considerations, load can be linear, non-linear, it can be there can be balanced fault, there can be unbalanced fault, symmetrical system, unsymmetrical system. So there are various considerations, and there is phase jump. Whenever there is a voltage sag happens, there is phase jump in the voltage. So that's why the controller must be smart enough to control the magnitude of voltage as well as the angle of the injected voltage must be compensated by the DVR. So most of the researchers have designed the 3-phase controller. They are very effective. they can compensate the magnitude as well as the angle. But what I have seen that particular controller is not suitable for single phase system. There is single phase port. Some of the controllers may not be suitable, but that is my opinion. It may not be suitable for the double network for that. That's why I have considered the controller must be applicable for single phase system as well as for three phase system, three phase 4 wire system. So it must be smart enough. That's why I have model the single phase as bridge inverter, where this is the DC link. Whenever there is VSI injects the voltage, it is in the form of MVDC, where VAB is the actual voltage, M is the modulation index. The modulation index is 1. It will inject complete voltage. Due to this switching frequency, there is repulse. That I have connected the LC filter. Initially, I have taken this RL value, that the inductance resistance value is 0, negligible, and I have modeled this. I have considered the two various half bridges. From one, it is alpha current is flowing, and from the second half, beta current is flowing. When I have modeled this edge bridge, half bridge inverter, and both these are both actual voltage, actual current, and the fictitious current. I have considered beta as a fictitious current, and both these actual and fictitious current, when they are combined, it will make the edge bridge. So through the derivation, I come to the conclusion that I can model the single phase edge bridge inverter in the two separate parts, because the alpha component has that decoupled both these alpha and beta component, because alpha has the effect on beta and beta has the effect on alpha. So this is the stationary reference frame model for single phase edge bridge inverter. There are again model for in the rotating reference frame. When I have modeled in rotating reference frame, I have used the chain reaction, and I have come to the conclusion that the D component current has the effect due to the Q current, K axis component, and the D component has the effect on the Q component current. So that's why we have to separate both these components for the effective controlling of the device. Now there is one more very important factor that I have faced difficulty from the single phase to two phase conversion, because the three phase system, three phase can be converted into two phase alpha beta, and from the alpha beta to DQ with the Clark and Clark transformation. But in single phase, as I have presently with only one phase, so that's why I have delayed this signal. I have sampled the signal at 20 kilohertz frequency, and for one cycle I have got the 400 samples, and I have delayed with the 100 samples, so that quarter cycle delay has been implemented to the actual signal, and this actual signal is delayed by quarter cycle, that is the 90 degree, that is the time delay method. I have used the time delay. There are various methods. There are phase delay method, time delay method, lag rate compensators are also there, but I have used the time delay method. I have delayed by sampling the signal, and this is the actual signal. This is nothing but V1 is the actual signal, V alpha, and this is the delayed signal. This is the fictitious signal at 90 degree, the actual signal, and power transformation has been implemented with the help of single phase discrete clearer, and so that I can get the fixed value VD and VQ. This is in the stationary domain. I use the single phase DVR like this is the resistor bypass switch, which is used for the internal protection of this edge bridge inverter. The DC link is connected with the energy storage device, and this is the bypass switch. Either I can make it the standby mode or the active mode. Whenever there is the SAT, the mechanical switch gets open and it is directly connected. The complete system is directly connected to the system, and it will protect the critical load from the voltage-based power quality problem. How it operates? Whenever there is a fault at the other node is not shown over in this. So there is a voltage drop in the PCC voltage, VT terminal voltage. So I have to maintain the load voltage. Again, this effect is on the load voltage. So I have to maintain the load voltage to a desired value. So that's why I have to inject a particular voltage at a particular angle. And this is the complete system which will control the voltage and angle injected into the system. Due to this complete DVR system, there is the injection of impedance with the help of a DVR. So because there is a power loss in the switching action, there is power loss in the inverter, there is power loss in the transformer. That's why that voltage is also considered in the control action. So that's why this is connected in series with the injected voltage. So this is the inverter injected voltage, and after removal of this drop, I will get the actual injected voltage. These are the power flow. There are different considerations. If there is active power, then the active power, maximum active power flow from the supply. There is lesser active power flows from the supply. But whenever there is a sag, if the voltage sag, there is a decrease in the voltage, then the active power supplied from the system will be less, and that will be supplied by the DVR. So that combination has been shown by this controller. Now the analysis for the injected voltage, anchor and active power. This is the injected voltage. This is the load voltage. Whenever there is a drop in load voltage or supply voltage, it will jump to a certain angle then, and we have to inject at particular angle alpha. So this is the reference axis. So these are the equations which are governed with this. Certain trigonometry has been implemented of the, and from this V injected, and angle injected has been computed. This is the case where this theta L, where the phase jump is equal to the power factor of the load. If this is the case, this is the V injected, alpha injected, and the power injected. Power injection will remain same because there will be no effect of the phase jump into power injection. These are the various data that is find out. And from the injected power, injected voltage, there is, see here, this is the case where decrease in the voltage from 0 to 1, there is injected power. Here. Now here there is no phase jump, first case. When there is no phase jump, see, when power factor is 1, the injected voltage, there is 20% decrease in the voltage, same is the amount of active power injected by the DVR. But if there is a phase jump in the system, then the active power injection goes on for power factor. If power factor is 1, the injected active power will be same. If power factor is lesser, then injected active power goes on increasing. Okay, if there is a phase jump, this is without phase jump, this is with phase jump, so active power injection goes on increasing. So where this is the case, injected voltage versus decrease in the voltage. So for all the case, it does not depend on the power factor of load. Okay, whatever may be the power factor, injected voltage will remain constant for any power factor. But if there is a phase jump, that there is a 20% decrease in the voltage with a phase jump, then injected voltage goes on, will be higher. For 10% decrease in the voltage, you have to inject around 29% voltage in the system. That means there is a higher voltage injection. That's why we need a higher rating of the DVR. Okay, that's why the cost of DVR goes on increasing. That's why we have to minimize this. There should be minimum phase jump that should be happen in the system. These are the cases where I have considered for this case, the second case I have done for this case, when the power jump is equal to the power factor of load. In that case, I have to inject a voltage. Then see here, if there is decrease in 20% in the voltage, there will be no injection of power. Then power factor is 0.8. Power factor is 0.8. Low power factor is 0.8. Up to 20% decrease in the voltage, there will be no injection of power. But see here, there is decrease in 10%. There is rapid increase in the voltage injection. That means higher rating of voltage is needed. This is the angle injection. For unity power factor, there will be no voltage injected by the DVR. See here. For unity power factor, there will be no injected voltage by the DVR. So there are various compensation methods, in-phase compensation method. This is the source voltage where there is decrease in the voltage, that is V sag. This is the source voltage, decrease in voltage V sag. So that are they are derived into components, D component, Q components. So this V sag is VD sag and VQ sag. So this is the injected voltage. If we have to inject the voltage in this fashion, then there is a, we can compensate the magnitude only. We cannot compensate the phase. So due to this type of injection, there will be lesser value of injected voltage required. So we can reduce the rating of the DVR. But there can be various other loads which are more cost effective due to phase change, like the systems, computer systems, or the ASD. So that's why there is another method, energy optimized compensation. We can compensate at 90 degree. See, this is the sag in the voltage. We can compensate at 90 degree to current. So this is the only reactive power compensation. So there is increase in the voltage injection, but we don't require any active power injection into the system. So we can compensate for a longer duration of voltage sag. This type of compensation can be used for longer duration voltage sag, but it needs needed higher voltage injection. That's why the rating of device required will be larger. There are the third compensation method. This is the pre-sag compensation method. This is in-phase compensation method, and this is the energy optimized compensation method. So this one is the best compensation method. The existing DVR controllers proposed by some researchers using SRFT theory are three-phase based and mostly works on pre-sag compensation, where PLL has to freeze to obtain the pre-sag of the voltage bus in digital simulation. And also for hardware implementation, it is difficult to freeze the PLL. Also the DLL, DC link voltage of inverter is not controlled separately, which creates harmonic at the load side. Furthermore, the single-phase SRFT based controller for DVR is less reported in any literature. That's why I concentrated on SRFT based single-phase controller. Now, most of the controllers where we have to lock the PLL when there is a sag. So, when I have to inject a voltage at this particular angle, I have to freeze this sag. Okay, but I have done the phasor analysis. I have to inject the voltage in such a fashion. So through the trigonometric analysis, I have done all this analysis. Where alpha, injected voltage, this is the reference phase, reference axis. Injected, this angle is not shown. Alpha is the theta pre plus theta injected. Okay, so theta, this is the pre angle. So this is the parallel line with this reference axis. This is the reference axis. This is the theta pre, this is the theta pre angle. And I have to get this theta injected. Theta injected can be obtained. This is the VD pre, total VD pre minus VDQ. Similarly, this VQ pre is 0. Initially, I have considered the voltage on the D axis only active power is present, no reactive power is present. That's why no VQ pre is present. So VQ pre is 0, VQ pre minus VQ sag. Now, this is the consideration with the losses. I have considered the loss in the line, so that's why this is theta injection to the system. And this is the controller. I have designed the controller on the phasor analysis, single phase to ABC transformation. There are two controllers. The inner controller is based on the for the transient analysis, and the second is for the improvement of steady state error. So here fundamental components have been derived. It is compared with the reference value, injected value. It is compared this injected voltage. This is the closed loop. Again, the injected voltage too on the load side. Both are added together. DP components are converted into single phase component. The harmonics are removed by the LPF filter. The injected voltage, reference injected voltage is again compared with the actual injected voltage, and the error is observed, and it is minimized with the third PI controller, and the minimized error of the injected voltage is again compared with the reference value. Since this third controller, PI controller is implemented in the controller just to minimize the size of the transformer, to minimize the saturation in the transformer which we are injecting with the injection transformer. And this is the injected voltage, both are added together. For supply voltage, for load voltage, both are added, and these generate the sine and cos. and this angle is added in the sinusoidal PLL angle. These are the equations that are derived from the phasor analysis. This is the single phase system consideration for the single phase. This is the fault on the other phase. Line. These are the parameters for single phase system. This is the actual controller circuit, control concept, system representation. This single phase 325 peak voltage 50 Hertz. The other load is 230. This is just considered for the design of the prototype model. Just I have to design the prototype for this. That's why I consider this data. This is the system representation with control concept and DVR. Here I need three values: sampling and hold of the terminal voltage, load voltage, as well as DC voltage. These are the results. The sag is created at 0.05 second for near about 6 to 7 cycles. This single phase fault, and here it is near about 55% voltage sag is created by 1 ohm fault resistance, and this is the injected voltage by the DVR. From these result, I can comment that the load voltage is restored to the desired value, but the response of the control is a little bit slower. It is compensating the voltage at near about 1 to half cycle. So it is a slower controller. So this is the alpha beta phases of the terminal voltage. See there, this is the alpha phase. The fictitious phase is created exactly at 90 degree phase. This is the beta phase, and this alpha beta are converted into DQ. DQ components are constant because I consider the linear load. This is the linear load. The current is linear. There are about 4 ampere current. There are about 3 to 4 ampere current. This is the DC line voltage constant when they are compensating the device. The sag is a little bit slower because the controller is a little bit complex. It is based on the feed forward and feed back control system. The actual injected voltage and the reference injected voltage both are nearly same. So from this analysis, I can comment that the DVR is
voltage.
This is the voltage. Here, voltage injected voltage is nearly about 200 volt. This is the reference injected voltage. This is also nearly about 200. These are the results for non-linear load. Similar type of results are obtained for the non-linear load. The current is non-linear in nature. Non-linear nature of current. But see here, there are certain up and down peaks are present in the DQ component due to this non-linear load. And see here, when there is a DVR action, this little bit transients can be clearly seen at these, and here at the end when the DVR is disconnected from the system. These are the similar type of results for the non-linear load. The second control is based on the instantaneous PQ theory based controller. The single phase is power can be the product of voltage and current, where three components alpha, beta, and rho. But in the single phase, there is no O component. That's why the active and reactive power are governed by only alpha and beta components. These are derived, and active power is the addition of DC component as well as the harmonic components present in the supplies. Similarly, the reactive power components are both DC component and the harmonic components. So these are derived that the actual injected voltage along the alpha axis, along the beta axis, these are derived, and they will depend on the current, alpha current and beta current. So these are derived. So the current has been converted from single phase to DQ, single phase to alpha beta to DQ, and the harmonics which are present in the current due to non-linear current, that are minimized with the NF filter. Going RF filter, most of the researchers have used the NF low pass filter, but the cutting frequency is less. That's why it gives more noise, and the response time is a little bit slower in the LF filter. And these DQs converted into single phase, that gives the fundamental components of load current. due to non-linear load. So I have to, and again I have to find out the with this the fundamental component of alpha, beta current, the injected active and reactive power these components, and these both components are separated out, DC component and the rest of the components, and this as I have present with only one phase, alpha phase, that is the actual phase. I don't have the fictitious phase. Fictitious phase is not present. That's why the injected voltage in the line will be only with the help of alpha phase. That's why this is with the alpha phase. This is the controller based on these instantaneous peak to 3D based controller, where I have to inject the active power. This is the I alpha, Vs alpha, I beta, Vs alpha, I beta gives the P active injected active power component, and these LPF is used to separate out the harmonic components from these. As I have used the fundamental component load current, which is already derived, extracted fundamental component that's why the harmonics are in the present in the current that's already removed from the controller. This controller has these parameters, where DC link voltage is around 5 millifarad, switching frequency is 8 kHz, and sampling frequency is 20 kHz, and 250 RMS value. The sag is created again at 0.05 second for near about up to 0.3 second. It is near about 40% sag the value. So, sorry, 50% sag has been created. The DVR is injecting voltage more than at 100 because it is the pre-sag compensation method. It will maintain the desired load voltage. So I can say that this controller is robust enough to maintain the desired value at the load side, and it is much faster as compared to the earlier controller. This the DC link voltage will remain constant. This the load current is linear in nature. Alpha beta generation of alpha beta components with these. See the ID and IQ components. ID and IQ components are constant. So active power supplied by the source during sag, the active power is decreased to 50%. Since the 500 watt is the active power before the compensation, before the sag, after sag it is decreased to 250 watt. So the DVR is compensated to 500 watt. This is the active power. 250 watt is supplied by the DVR. This is the reactive power. Reactive power is dropped to 0 to minus 200. This 200 watt, and this DVR is this DVR has itself has a nature to compensate for reactive power compensation. Now the control, this is for the results for non-linear load. The current is non-linear in nature. The DC link voltage remains constant for non-linear load in nature. See here, due to the presence of non-linear load, the ID and IQ components has this nature. So that's why I have to consider the MF filter to remove these. So MF filter has been implemented to remove these distortions which is present in ID and IQ components. Now they are the steady DC value, ID and IQ. This is the active power supplied from the source to non-linear load. The active power is maintained to constant value. The voltage injected by the average value is also calculated. Average value is near about 110 volt. This is the 400. This is a little bit decreasing. Since I have to optimize the energy storage, the reactive power injected by the DVR is nearly 40 watt. It is maintained a constant value. This is the average load voltage. Load voltage is maintained constant. Average load voltage is maintained constant to 200 volt. Active power is maintained to constant value. Reactive power is also maintained to constant value. Now the hardware design circuit. In the hardware design, single phase system is considered as a distribution side. The transformer, coupling transformer is connected to 30 by 9 volt. The load is considered, this is the R load. Load is a bulk of 40 watt. R load is connected with the transformer. It is a series load, RL load, and this the relay circuit is connected. Initially, the transformer is not into the system. Whenever there is a sag, the transformer gets connected to the system with the help of the relay. and the filter is used to filter out the harmonics which is present due to the switching action of the DSI. Battery of 12 volt, 7 ampere hour is used, which provides the power, active power to the DC link. Driver ICs IRF 533P is used for driving the switches. This is the given to the DSP. DSP microcontroller has been used to drive the and the same supply, 230 volt supply is converted into a step down to 9 volt, which is rectified and the regulated with the IC 7805 given to the DSP microcontroller, and this microcontroller they have put the programming to inject the voltage. SPW method has been used to inject the voltage in this line. This is the hardware model HB MOSFET based inverter DSP microcontroller rectifier circuit. This is the rectifier circuit. 12 volt battery. This is the battery. This is the coupling transformer, injecting transformer. Driver ICs. These are the two driver ICs for the 4 switches. This is the step down transformer to make it applicable to the controller as a power circuit, and the this circuit. This is the inverter output voltage can be seen when the inverter is in action. These are the sag is created, 50% sag is created, injected voltage 50%. See here, this is the compensated load voltage. Load voltage before fault is near about 9 volt. When the fault is created at this instant, it is dropped near about 90% of the value. Generally, the sag is around 30 to 40%, but I have created the 90% sag. So it is compensating it is the hardware based, the controller is little bit slower. So it is compensating after 2 to 3 cycles. It is compensating the voltage, supply voltage, but it is compensating around 65 to 70% voltage only. As the battery is decreasing its value, it is not compensating to a exact value. So compensation is little bit slower, little bit less. These are the results for the non-linear load. Non-linear load is present. Here the non-linear triac-based load is corrected. Triac is corrected. This is a non-linear load. It gives you this type of results. And this is supply voltage. This is the injected voltage by the TVR. And the third one gives you so these are the results for non-linear load. Here we can the certain transients and the spikes can be observed in the load voltage, but it is compensating to a desired value. Now this is the third controller. Since both these controllers, 3-phase controller as well as single-phase controller, and many of the researchers they have not considered the distortions on the load side, so on the supply side. So both these controllers are giving a little bit sluggish response for the distortions which are present on the supply side. That's why I considered the third controller, and this is very robust and a novel controller. It only requires the reading of these only 2 components, terminal voltage and the DC link voltage. Only 2 signals has to be measured to control these load voltage. So these are the equations. I will not go through the details of this, but I will give you the details. Terminal voltage, whenever there is a sag, you have to inject a voltage, so it will maintain the load voltage to constant value. These D and Q components are separated. Initially, whenever there is a sinusoidal voltage is present, then D component is not D component is 0. So reference load voltage will be exactly equal to the terminal D component, and whenever there is a Q component is 0, the Q component will be equal to load side Q component will be equal to terminal Q component. That D component has been derived, and Q component we can get from the peak value of load voltage. When peak value of load voltage is separated or subtracted from the D value, we will get the Q value. So, and the losses are also considered. Losses are removed from the terminal voltage. There are different processes that is taking place in the line. Again, there is single phase to ABC, alpha beta to DQ, MF filter has been used. These are already the DC value, and it has again averaged out to get the exact constant DC value of the supply side. So DQ is converted into single phase from the inverse transformation with the help of PLL. These are the controller, third controller, where fundamental component has been, terminal voltage has the certain distortion, supply voltage distortion, that is the extracted fundamental component, single phase. And for fundamental extraction, separate SRF theory has been used. And this, again single phase is come to DQ. So D component is compared with these PI control, both these components are separated. This gives the loss, power loss that is taking place. LPF has been used during the injection. The DC link voltage has certain spikes. That spikes has been removed with the help of a LPF filter. Its cutoff frequency is around 0.7, so it gives you better response. Both these are added. D component, you can get Q component by removing it with the peak value of load voltage. We can get Q component. Both DQ components are added. With the help of PLL is converted to single phase. This gives the instantaneous value. This compared with the reference value, and this is the third PI controller to minimize the saturation of transformer, that is given to STP. Pulses are minimized. These are the data which is considered for the third controller. Now see, in the third controller linear load with distorted supply without sag. Without sag, the fifth and seventh harmonics are inserted in the supply voltage. The injected voltage, certain transients can be observed. Now in this case, the DVR is in action from the zero instant. The DVR is in action from the zero instant. The transients can be observed. Now the injection voltage has settled down to its normal value. Injection is proper. The compensated load voltage is maintained at desired value. So it is the robust controller for the green. Only it is working now. In this case, it is working as an active power filter. API. Without the this is the alpha beta component with the distorted supply. See, with the distorted supply, DQ components are not constant. DQ components are certain variable value. So these variable value of DQ components are removed with the help of MF filter. The load is a linear load, so current is linear in nature. DC link voltage is nearly constant. This is the actual injected voltage with the certain transients where the DVR is in action. This is injected reference voltage, both are nearly same. So from these results, I can comment that this controller is robust enough for the non-linear load as well as linear load, non-linear load, as well as for the distorted supply condition. Now these are the linear load with distorted supply. Sag is created from 0.7 to 0.2, near about 8 cycles. Sorry, 1 to 2, near about 7 cycles. This is the injected voltage by the DVR. Certain transients can be observed during the switching action of DVR. This is the load voltage is maintained to desired value. These are the alpha beta components. These are the sag value of a distorted DQ phase of supply voltage. The load current is maintained to constant value. Again, for non-linear load with distorted supply sag value. Now see here, before the compensation, the TSD due to the fifth and seventh harmonic is around 25.48%. With the IEC 555 IEC standard 519, I have minimized the TSD to 3.434%. So it is much lesser as compared to the IEC 519 standard. Now this is the for non-linear load with distorted supply. Again, this is the sag is created for around 7 cycles from 0.05 second to 2 seconds. This is the injected voltage by DVR. This is the compensated load voltage. Load voltage is maintained to desired value. Phase is maintained. Magnitude is maintained to constant value. These are the non-linear nature. It can be observed that the current, that the load is non-linear in nature. The alpha and beta component are 90 degree phase shift. Alpha beta converted to DQ. Since certain variables, DQ components are variable in nature, because the supply is distorted as well as the load is non-linear in nature. That's why MF filter has to be introduced to minimize the variable that is present in the, and it is maintained to a constant DQ value. Is the constant DC link voltage is maintained? Is the injected actual voltage, injected reference voltage, both are same? And the TSD before the SAG value, before the SAG is around 25.34%. During the after the compensation, it is minimized to 3.4%, which is much lesser as compared to the as required by the IC 519 standard. Then I have three identical controllers are connected for the 3 edge bridge inverter. These are the distortions in 3 phases. This is only the distortion. Now the DVR is providing only active power to the system, not reactive power. So it is acting as an active power filter. It is the injected voltage. See the performance during the SAG. This is the 3-phase SAG. This is the distorted 3-phase supply. Around 60% SAG is created for near about 7 to 8 cycles. The compensated. This is the compensated load voltage, and load is see the DVR action. DVR is starting from from 0 instant. DVR is in action, so the transients are reduced and the load is maintained to a proper value. This is the injected voltage during the when there is no SAG. It is giving the transients. It is taking near about 1 cycle to be in action. The TSD is again reduced in this case also to 4.34%. The conclusion from all the controller analysis, there are 3 controllers as been designed by DVR. It can be concluded that the SRF based controller for single phase DVR shows the robust performance. For voltage based power quality problem, the modified single phase SR theory with utilization of MF filter has been used for obtaining the fundamental frequency component of distorted supply voltage. Accordingly, a novel single phase control for DVR has been mathematically analyzed and simulated for mitigation of voltage sag and the sinusoidal and a distorted supply condition. The simulation results promptly validates the theoretical and mathematical analysis of the proposed control of DVR. The voltage based power quality problem has been improved with the utilization of proposed single phase controller for S-bridge VSR. The controller is based on single phase APC to DQ. By all the analysis, it can be concluded that single phase controller for DVR can be applicable to single phase, 3-phase, 4-wire system. The controller indicates the improvement in the transient as well as steady state performance. It can work for symmetrical or asymmetrical fault conditions, also for linear and non-linear load conditions. And the most important is that it is the cost effective solution for the DVR. So my contribution from this proposed work, initially the focus is given to 3-phase controller, which design topologies, unbalanced voltage sag, mitigation need of energy storage. Thereafter focus on the control design is made towards the design of controller which is suitable for mitigation of symmetrical and symmetrical voltage sag with restoration of voltage at the same phase before the occurrence of sag. In the second stage, a 3-phase controller for DVR with 3-leg VSR operating on feed-forward control technique is designed and investigated. The SPWM method has been implemented. Simulation method has been carried out in MATLAB simulating. Thereafter, it is designed for multi-level VSI. In the third stage, modeling of single-phase SPW inverter is investigated based on SRF. In the fourth stage, single-phase control based on instantaneous reactive power theory. And lastly, it is designed for simulation as well as hardware results. And lastly, the novel single-phase controller which works on SRF theory has been proposed for the DVR. These are the now I have submitted one of the paper. I have got the first review in the JP Journal of Power Electronics SCI journal. Hardware results are expected. At that time, my hardware results are not present with me. I have got certain hardware results. I will modify this paper and again send it back to the reviewers. Same reviewers. These are the international journals where I have published the paper. One of the paper is published in Elsewhere, Energy Procedia, Science Direct. Second is the JEMA, Journal of electromagnetic analysis and application. Uh, this is based on modified SRF DQ theory based controller for dealer getting into voltage size in case of non-linear load. This is SRF based controller. This is the phasor based controller, phasor based analysis. In the this is the unpaid journal. This is the IGCTA. This is the Scopus Index journal. Robust based. This is the RJR journal. The research journals I have published the papers. These are the conferences I have attended in the VIT, MIT Gopal IEEE conference. This is not published yet. I have presented the paper at Gopal IEEE conference. This is the second paper I have, the first conference in TechCon, VIT Chennai. These are the other conferences I have attended. These are the references which I have referred for my research to the PhD work. Thank you very much, sir, for patiently listening my work.
So last attempt for audience questions.
Your conclusion sheet, conclusion, that slide.
Like a bullet you should have put it.
Yeah.
It is like an abstract where people write your conclusion.
And second,
Next one also. Next page. This. Some bullets like that is better.
perhaps the word proposed is not sitting there. Now you have completed. No?
I have completed, but I have not submitted the
You know,
some of the work I have not submitted.
whatever you have done,
That's why I am very clear.
you know, a common reader would prefer whatever you have completed should be listed separately, conclusions, and whatever you feel that can be extended under future scope. So your, if not exclusively mentioned, scope of future work should be separately listed.
Thank you. That's what I will. I have not shown you.
In your final.
Thesis formats are like that. Because the last chapter where conclusions to put it, some future also, some user. And it should be like a bullets.
Right.
Sir, can you please explain a little bit more about MAF filter?
Sir, this MF filter is average, works on average value.
What is the configuration? Whether it is pi filter or combination of LC filters?
It is likewise LPF filter, but it gives you decimal noise and the response of the LPF filter is more faster as compared to the LPF. It minimizes the, it makes the output more constant, gives you more constant.
You are filtering the signal or actual power?
Signal, what is
Voltage signal. You are filtering. And what is the size of LF and CF which you have mentioned in inverter? What is the component of
LF?
LF and CF in the inverter, single phase inverter?
Various values are, for various controls, various values are. For these it is 5 millihenry, 20 microfarad. LF and CF.
Is ferrite core? Is it ferrite core or iron core?
Filter? Iron core.
If iron core, it will consume all
In the
power.
transformer, in the coupling transformer, injection transformer, I have used the farad core, but the use of farad core is giving much inductance.
Ferrite core will have less interest.
But I don't know why it is giving more inductance. I have used the farad core.
How you have taken the feedback signal? How the feedback is, how much proportion
In the hardware, I have based on the programs. I have not taken the signal for the supply of loads. I have just programmed therefore the SPW technique. And on the initial base, I have done the hardware. I have not I have not used the voltage sensor, current sensor, and amplifiers for getting the analog to digital control.
Some hardware you develop, no diagnosis. So,
I have shown the hardware. Is the hardware circuit. I have considered the supply line as a distribution line, 230 volt 50 hertz supply, and I have connected. I have considered the RL load, the
Is it
residual
three
load
phase? Is it three phase?
is single phase based. It is prototype model.
So, makes a lot of difference between single phase and three phase. Single phase, three phase, major difference.
Yes.
Okay. Anyway, some hardware.
These are the results. This for the non-linear load, supply voltage, injected voltage and the capacitor load voltage. Certain transients and ripples are observed in the load voltage. I can improve that.
See, these are all commercially available, DVR.
Yes.
So device is available, and maybe power quality problems in industrial area also are there, and people have used also DVR itself. What you feel your contribution?
So these controllers,
These are all existing filters existing. So
many of the controllers are based on instantaneous values. Most of the controllers are symmetrical, based on symmetrical component based. I have used the SRF theory, which works on average value. So it gives exact detection of voltage side, so that the voltage injection is minimized, power injection is minimized, and the energy storage device can be minimized. Size of the energy storage device can be minimized, so that it can be cost effective.
there is a really something which, see, essentially these things, like your harmonics are brought down, and the devices which are compensating, the size is brought down, cost is brought down, this type of things, right? So where it will be, if your design is adapted, where it will contribute? Cost wise it will reduce, or what is the performance wise it is better,
Performance.
but it is only single phase unit. How you prove it?
So we can implement it. PLL works properly. PLL works properly, then it can be implemented to three-phase system also. Or any type of fault condition. Single phase fault, symmetrical, unsymmetrical, any type of. Three separate identical controls can be used for each phase.
And this whatever power quality problems, you listed so many problems. Will it solve all those problems?
I have concentrated on the SAT,
Only
harmonics, flickers, spikes. On that power quality problems I have concentrated.
So many other things are
There are
show the triac non-linear, please. The second one,
Yes, sir.
how is the firing, it is firing angle control. Triac means firing
Firing.
angle control. How that waveform is just opposite to that firing angle. The center one.
Better one.
Center one.
So, sir, this is the
Weaker.
this is the injected voltage. It is not showing exactly the firing angle. Due to non-linearity, the waveforms are very much distant.
The load voltage.
This is the supply voltage. Middle one is the sag voltage.
Middle one is sag voltage.
Sag decreasing the supply voltage. And third one is the injected, compensated load.
But voltage you said close to triac is like that.
Yes, sir.
But I think that will be opposite to that because triac will not turn on at zero crossing. This is turning on at zero crossing. It should be just opposite to that. It should turn off at 180 degrees and turn on at alpha. This is turning on at zero crossing and turning off before 180 degrees.
I programming where is
Just opposite to that. I have got a little bit doubt on that.
it should be fired at this instant. It should be fired at that instant. It should be fired at this instant. Here. It is slower. The control is slower. That's why it is taking time. The hardware. And make sure. Okay. Thank you, sir.